for the system having the open loop transfer function g of s into h of s is equal to k divided by s into s plus 1 s plus 2 into s plus 3. Okay, this problem is solved in both Anand Kumar as well as Bakshay textbook. Correct. Fine. So you are supposed to plot the complete root locus. Okay. So over here itself, I'll be discussing the various rules. Step 1 or rule 1, root locus is symmetrical about real axis. Step 2 is about open loop poles and zeros. Right. So we have number of open loop poles. Okay, we have 1. Okay, let me use a different color. So this is your first, this is your second root, this is your third root, and this is your fourth root. So the roots of the denominator polynomial of g of s into h of s is basically the open loop poles. So there are 4 poles, right? Okay. And are there any zeros? There is, I mean, the numerator is independent of yes. So zero count is 0. Okay. So number of open loop poles are 4 and number of open loop zeros are 0. So this leads us to the comparison of P greater than 0. So number of poles are greater than number of zeros. Therefore, number of root locus branches. So n is equal to number of root locus branches. Okay, is equal to P is equal to 4. So that means to say this particular root locus will have 4 branches. Okay, so this is the prediction we are doing before sketching the root locus itself. All right. Then you can write the starting points and also the terminating points. Okay, at terminating points, what do you have? You have zeros. At starting points, what do you have? You have poles. So basically you have 4 poles, right? So starting points can be written as the first factor. When you equate it to 0, what do you get? The root value as 0, comma. The second factor, when you equate it to 0, you will get the pole value as -1, -2, and then -3. So these are the starting points. Okay, remember P is equal to 4. So 1, 2, 3, 4. Terminating points. Do you have any zeros? We don't have any zeros, right? So you can just put dash. That implies the terminating points are 0. So what is the meaning of this particular, analysis? So the meaning of, or the rather outcome of, this particular analysis is that all the 4 branches of the root locus move towards infinity along the asymptotes. Okay, so you need to take the help of the asymptotes to project all the branches of the root locus, moving towards infinity. Okay, why they move towards infinity? Can anyone tell me? Because there are no terminating points. So this pole is not having any terminating point. So as this pole, the other poles as well. There are no zeros. So if there are no zeros, then all the branches of the root locus will move towards infinity. So that's the understanding of step 2. Okay. Step 3 is about prediction of root locus on real axis. For this, what we will do, we will draw a pole zero plot, a simple pole zero plot. And remember one thing, step 3 is applicable to only on the real axis. Okay. For imaginary axis, we cannot apply step 3. So just draw the pole zero plot. I myself had confusion while discussing about step 3 in the previous class. Okay. So pole zero plot we will do. So you have a pole at origin, pole at -1, pole at -2, pole at -3. Okay. So what you have to do is you take a small section uh, just on the right hand side of the pole. Okay. Just keep an imaginary, dotted line just right to the, each pole and 0. Okay. And then count number of poles and zeros falling on right hand side. Okay, if you keep this reference line and if you start counting, the number of poles and zeros which are falling on right hand side of this particular section, say section 1, you see that there are no poles and zeros present on right hand side of section 1, right? So in section 1, count is 0. So 0 is even number, right? If you get the count as an even number, then we say the prediction as NRI. So that means to say this entire positive real axis is NRI. Okay, so you cannot have any root locus movement along the positive real axis. Okay. Now let us go to section 2. And taking section 2 as the reference, you count how many poles and zeros are lying on right half of section 2. So if you count the poles and zeros which are falling on right hand side of section 2, you see that the count is 1, right? So count is 1, odd number. So there is RL. Okay, when you get RL, what I will do, between section 1 and section 2, you can say that there is root locus. Let me slightly thicken the line so that visibility gets improved. Okay, so RL, here let me write RL. Okay. And then you move on to section 3. Count how many poles and zeros are lying on right hand side of section 3. You have one pole and you have second pole. So the count becomes 2. 2 is even. So when you get even count, it becomes NRL. So you don't have any root locus branch between section 2 and between -2 and -1. So this part you can write it as NRL. Okay. And then you go to section 4. Count how many poles and zeros are present on right hand side of section 4. 1, 2, and 3. So you will get count as 3. 3 is odd. Hence you can say that there exists a root locus branch. So between section 3 and section 2, you can say that there is root locus branch. So between -3 and -2. You can write that. There is R. Okay. And finally, what you do at some distance, let's say -infinity, you create the endpoint. Okay, and let's call that endpoint as section 5. So taking section 5 as reference, you count how many poles and zeros present on right hand side of section 5. So basically, you're just observing, standing at -infinity, and you are counting how many poles and zeros are present on right hand side of the section under consideration. So 1, 2, 3, and 4. So count is 4, 4 is even, and RL. So from -3 towards -infinity, your entire real axis going to be NRL. Okay, so that means to say you cannot have any root locus branch present between -infinity and -3, and -2 and -1, and 0. Okay, this is 0, right? 0 and plus infinity. Okay, so this is the prediction. Okay. You'll understand the prediction when we calculate something known as breakaway point. Okay, so this step 3 also helps in validating breakaway point. Okay, breakaway point is nothing but the meeting point of two root locus branches. Okay. Step 4. Angle of asymptotes. Okay. So angle of asymptote, it's a formula based calculation. Theta is equal to, sorry, before angle of asymptotes, I think centroid, sigma. So sigma is equal to real part of poles minus real part of zeros divided by P minus Z, which is equal to summation of real part of poles. So what are the real parts of poles? 0, -1, -2, -3. Minus real part of zeros, no zeros, so you can just put it as 0 divided by P minus N. Number of open loop poles are 4, zeros are 0. So you will get sigma. So basically 3, 5, 6. 6 by 4 is minus 1.25. Six by 4, 1.5, right? Yeah, 1.5. So the centroid is located at -1.5. So what I'm trying to tell you is that here, over here, sigma is equal to -1.5 is present. Okay, so taking that as the reference, taking that point as the reference, you are supposed to draw the asymptotes. Step 5. Step 5 is angle of asymptotes. Theta. Are you guys with me? You're able to hear me, right?
Yes, sir.
Okay. So angle of asymptotes, theta. Theta is equal to 2q plus 1 into 180 degree. okay, divided by t minus z, where q is equal to 0, comma 1 till p minus z minus 1. So q is equal to 0, comma 1 p minus z minus 1. So p is 4, z is 0, minus 3. So the endpoint for q is 3. So basically q can assume the following values: 0, comma 1, comma 2, comma 3. So because 3 is the endpoint. Okay. So I think it's appropriate if we keep theta q, right? So we can find something known as theta naught. So theta naught for q equal to 0. How much we will get? Theta naught as 2 into 0 plus 1 divided by t minus z. P minus z is 4, all right? So 4 into 180. So 45. Okay. And then for q equal to 1, let us find theta 1. So theta 1 is 2 into 1 plus 1 divided by 4 into 180. So this is basically 3 by 4, right? So 3 into 180 by 4. Okay. So 180 by 4 is, we have already found, right? 45 degrees. So how much you'll get? 45 into 135? 130. 45 into 3, 135. Okay, then you find theta 2 for q equal to 2. So that is 2 into 2 plus 1 by 4 into 180 degree. 2 into 2 is 4, 4 plus 1 is 5. So it is 5 times 45 degree. 225 degree. Okay, and then finally you can take q equal to 3. That gives theta 3. So 3 into 1. Sorry. 2 into 3 plus 1 divided by 4 into 180 degree. So that's 7, right? 7 into 180 by 4. So 45 into 7.
315.
300. Okay, so these are the asymptotes. Okay, so what I will do over here itself. Okay, and one more thing. First and foremost thing, you are supposed to draw root locus in a graph sheet. All right, so internal exam, you have to take a graph sheet. External exam, graph sheet is provided in your booklet itself, right? So you must be, you you must have observed in the beginning itself, you are provided with a graph page, right? On one side you have semi-log sheet, and on the other side you have, the linear graph, the conventional linear graph. So in the conventional linear graph, you are supposed to plot the root locus. Okay, and in the semi-log sheet, you can plot the Bode diagrams. All right, so Bode plots are drawn on semi-log graph, and root locus problems are drawn on the normal linear graphs. Okay, now let me tell you how exactly you draw these asymptotes. So to draw these asymptotes, what you have to do is, okay, in your graph sheet, proper scale value you are supposed to take. What shall I do? Okay, later I will do. Let me go with other steps. In one shot, let me finish the graph. So step 6, breakaway points. So first definition. Okay. Breakaway points are nothing but the uh, point at which the two branches of the root locus meets. Okay. The point at which the two branches of the root locus meets. Okay. You can also say that at breakaway point, the system damping is 1. Okay. So at breakaway point, the system damping is 1 to some extent. Okay. Sometimes, you will be also getting the complex breakaway point. So let me not make it as a general statement. It is contextual, depends on the system type. Fine. So breakaway point is nothing but the point at which the two branches of the root locus meets. Okay. What is the understanding? Let's say, for example, I have a pole at the origin. Let's say I have some pole somewhere at -1. Okay. So when you apply rule 3, okay, you see that this part becomes NRL and this part becomes RL, NRL. Okay. So the region present between 0 and 1 is the valid root locus region. Okay. So what happens is that as you start increasing the value of k, okay, as k is increased from 0 value, the root location is going to change. The root location is going to change. You remember, right? In the very first class, I had demonstrated with the help of simple transfer function, right? For k is equal to 0, the root value was at origin. For k is equal to 1, the root was present at -1. For k equal to 2, the root got moved to -2, so on and so forth. So, as you start increasing the value of k, the root which is present at the origin gets displaced. Okay. Similarly, the root which is present at -1 is also going to get displaced. Now, the question is, can this root move in the right-hand side direction? No, because in rule 3, we have predicted that this right-hand side region is NRI. Similarly, this root present at -1, okay, can it move in the left-hand side direction towards minus infinity? No, it can't, right? Because rule 3 says that the region which is found on left-hand side of -1 is NRL. So NRL means no root locus. So you cannot plot your root locus in that particular region. So the only possibility to have the root movement is between 0 and -1. So what happens is that as you start varying the value of k, the root which is present at the origin, start moving in this direction. All right. Similarly, the root which is present at -1, it starts moving in the right hand side direction, because left hand side it cannot go, because on the left hand side direction you have another. So this is how they move. Okay. Then at a particular point, these two roots meet. Okay, at a particular point, these two roots meet, and beyond this point onwards, the root locus graph becomes complex. The root locus graph becomes complex. Complex as in the root which is present at, let's say, -1, gets into this complex region. Similarly, the root which was present at 0, let's say it is moving in this, downward path. So downward path is also a complex region. Remember, as per rule 1, root locus is always symmetrical about real axis. So I'm maintaining a perfect symmetry. What I get in quadrant 1 and 2, the same thing I should get it in quadrant 3 and 4, but in the mirror image sense. Okay. So, This point is called as breakaway point. Breakaway. Okay. So let us, look at the procedure to find the breakaway point. Okay. So procedure is very simple. So step one. Okay. This breakaway point itself has few steps. Okay. So let me write. Step one. Um, Form the characteristic equation. Okay. So what's the characteristic equation? 1 plus g of s into h of s is equal to 0. Okay, that implies 1 plus g of s into h of s is already given, right? So k by s into s plus 1, s plus 2, s plus 3 is equal to 0. So if you take LCM and if you equate the denominator to 0, you will end up in getting the characteristic equation f of s is equal to s into, okay, so this one I will open up. Okay. So what I will do, we will reduce our complexity, calculation burden. So this and this I'll multiply before and only. So this is s square into 3s into these two terms. Let me multiply together. So it is s square plus 3s plus 2. You're following, right? S square plus s plus 2s is plus 3s. 1 into 2 is 2. Okay. Plus k is equal to 0. Or f of s is equal to s square into s square is s to the power 4 plus 3s cube plus 2s square plus 3s cube plus 9s square plus 6s plus k is equal to 0. Or the characteristic equation f of s is equal to s to the power 4 plus 3s cube is 6s cube. Okay, plus 2 plus 9 is 11s square plus 6s plus k is equal to 0. So this is our characteristic equation. All right. Now, step 2. So firstly, you need to find the characteristic equation. Once you have the characteristic equation, you can go to step 2. So in step 2, what you write is rearrange the characteristic equation in the following form. Okay. So in the following form, as in you keep k term on one side and you bring your, I'm using small f because you shouldn't get confused with the capital F. Okay, the capital F is the characteristic equation. This small f of s is basically the function of s. Okay, so you'll have to rearrange the equation in such a way that you keep k on one side and you bring all the s terms on the other side. So how do we do that? You keep k on LHS and bring all your s terms onto the RHS side. Okay, so that is negative s to the power 4 plus 6s cube plus 11s square plus 6s. Okay, fine. So this is done. Step 3, differentiate k with respect to s and equate it to 0. So let's differentiate. So dk by ds is equal to 0. So when you differentiate, what do you get? Minus 4s cube plus 18s square plus 22s plus 6 is equal to 0. So obviously this negative sign is going to get absorbed, right? So basically you are left with 4s cube plus 18s square plus 22s plus 6 is equal to 0. Okay, let me highlight this equation as well, but with a different color. Now what you do, find the roots of this equation. All right, it's a third order function, so obviously you're going to have three roots, right? You are going to have s1, s2 and s3. So these roots are nothing but breakaway points. Okay. So these roots are nothing but breakaway points. So quickly you can find out the roots of this particular equation by substituting the coefficients in the calculator. So what values you will get? You'll get the values as minus 1.5, minus 0.381, minus 2.619. So these are the three roots. So okay, so observe that all the three roots are real, negative real. Okay. Now you have got three roots. Okay. Now your rule number 3 comes into picture in the sense check the validity. Validity using rule 3. Okay. That means to say, I mean, all the roots may not be the valid breakaway points. Okay, only few may be the valid breakaway point. Now, whether they are the valid breakaway points or not, okay, uh, that can be checked by applying rule 3, because rule 3 talks about existence of root locus on the real axis, and these are all real roots, right? So what we will do, let us try to place these roots in rule 3. Okay, if the root is getting placed in RL region, we will consider it as a valid breakaway point. All right, if the root is getting placed in NRL section, we will say the root is invalid. All right, so let's go back to rule 3 and let us start placing let's say we use some popping color. Okay, let's say this color we use. Okay, so what's the first breakaway point? The first breakaway point is minus 1.
Minus 1.5.
Okay, where is minus 1.5? Minus 1.5 is somewhere here itself. Okay, first let us place. Okay, the second one is minus 0.38. So minus 0.38 is somewhere here. Okay. And the third point is minus 2.61. So 2.61 should be there between minus 2 and minus 3. So somewhere here. Okay. Now we have placed the 3 breakaway points, but we see that out of 3, only 2 are getting placed in the valid section of the root locus, right? So this point is a good breakaway point because it is getting placed in the valid section of the root locus. So as the first point, correct? You look at the second point. So the second point, whose value is minus 1.5, is getting placed in the NRL section of the root locus. So straight away you can say that the breakaway point, which is located at negative 1.5, is an invalid breakaway point. You're following? Can I get quick yes or no?
Yes, sir.
Okay, so invalid. Valid. Valid. So this step 7 is something to do with the RH criteria. Okay, this step 7 talks about intersection of root locus with j omega axis. So this step basically tells us whether the entire root locus plot is lying on left hand side of the uh, complex S plane. Okay, whether it is lying on the left hand side of the complex S plane or not. Okay, so intersection of root locus with j omega axis. Okay, so for this, what you have to do again, it's a procedural way. First, you should have the characteristic equation, capital F of S. Okay, once you have the characteristic equation, uh, form RH table, and then look for marginal stability. Why marginal stability? Because at marginal stability, the roots of the characteristic equation, okay, will be purely imaginary in nature. So K mar, we need to look for K mar. Okay. Now, if you get K marginal as positive, okay, you can say that root locus intersects with j omega axis. On the other hand, if your marginal value of k is negative, then you can say that root locus does not intersects j omega axis, or in other words, entire root locus line left hand side of yes, entire root locus line left hand side of yes. Okay. Another way of looking at the things is when k marginal is positive, your roots are kind of plus or minus j omega. Okay. On the other hand, when your k marginal is negative, your roots, okay, going to be kind of plus or minus a. Okay. So this is purely imaginary. This is real root, right? Plus or minus a. Fine. Enough of talking. Let's find the values, then you will understand. Okay, so we'll create the RH table. For that, you should have your characteristic equation. So characteristic equation we have already found in the previous step, right? So I'll do it here itself. So what's the characteristic equation? S to the power 4.
4
Right,
plus
correct.
6x cube.
Yes. Then S square. Then S to the power 1. Then S to the power 0. Okay. The first coefficient is 1. And then alternate powers of S. So 1, 11. And then K.
Yes.
And then the missing coefficients. 6, 6, and 0. Right. So this is this could be the possibility. Okay. Right. So what we will do, first we will try to determine the value of K. So we know that for stability, for stability, 60 minus 6k by 10 should be greater than 0, right? Because for stability, we want to have the coefficient in the first column of RH table to be positive, or you know should have the same sign. So with which what you get is um, 60 minus 6k should be greater than 0. Okay, or 60 should be greater than 6k, or the limiting value of k is something like k should be less than 10. From s to the power 1 row. Similarly, from s to the power 0th row, we want k should be greater than 0. So for stability, k should be operated between this limit. K should be greater than 0 but less than 10. Any value of k greater than 10 leads to instability. Okay. Now, what happens if you were to set k is equal to 10? So this is called as the marginal value. The moment you set k value as 10, you know, your first element of s to the power 1 row becomes 0. Correct. 60 minus 6 into k. And how much you are setting k as 10. So 60 minus 6 into 10, that is 60. So 0 by 10 is 0. So you will get s to the power 1 row as the row of 0. So this is what I was trying to tell you. Okay. So at k marginal, you constitute an auxiliary equation. So auxiliary equation is created from a row which is sitting just above the row of zeros, right? So from a square row, you are supposed to create the auxiliary equation. So what is it going to be? 10s square
S square plus K.
plus k. So let me write it as k marginal. Okay. So you can say 10s square plus 2. Okay. Now, roots of the auxiliary equation are nothing but the dominant roots. Let's find out the dominant roots. So what you do, equate a of s to 0. So basically 10s square plus 10 is equal to 0 you are trying to do, right? That implies 10s square is equal to minus 10, or s is equal to plus or minus under root minus 1, which is nothing but plus or minus j omega. So you look at this statement. In the beginning, we stated that if k marginal is positive, the root nature going to be plus or minus j omega. So in this given problem, we have obtained k marginal is, positive, right? And we have obtained the root value as plus or minus j omega. Okay, this omega is 1. We can say plus or minus j. So what is the conclusion? The root locus cuts the j omega axis at plus or minus 1 value. Okay, that means to say this is your intersection point with j omega axis. Okay. So that's the 7th rule. And then you have rule 8. So rule 8 talks about angle of arrival and departure. Okay. Now Let me write it in a different color. So this rule 8 is applicable only if only if a complex pole or zero is present in g of s into h of s. Okay. So rule 8 is applicable only if a complex conjugate, okay, I will say complex conjugate. That makes sense because they appear in conjugate. If complex conjugate pole or zero is present in the open loop transfer function g of s into h of s. Now, in the given problem, you don't have any complex conjugate pole or zero, right? All poles are real in nature and there are no zeros. So, for this problem, it is not applicable. Hence, you can ignore it. Okay, I'll solve a problem maybe in the future class wherein you may have to apply a rule 8. That time, let us discuss.
Okay, now let us draw the root locus. Okay, first what we will do, we will mark the real and imaginary axis. Okay, let's say this is your plus j omega axis, and this is your minus j omega axis. All right, and this is your minus sigma, and this is your plus sigma. Okay, so first let us place the poles and zeros. We have a pole at origin, and then we have pole at -1, then -2, and -3, right? So this is 0, this is -1. Okay, we will do one thing. We will take slightly a bigger scale. So let's say this is -1, -2, and this is -3. Okay. Similarly, this is your J1 and this is your J2. Okay. And this is your J1 and J2 is somewhere here. No problem. Let it be. Okay, so basically you will have to take uniform scale along x-axis and y-axis. Then only you will get um, a proportionate graph. Okay, or else there will be some compression along x-axis or y-axis if at all you select a non-linear scale. Okay, so what I've done is I've taken a linear scale in which I have taken 2 revisions is equal to 1 unit. All right, so that's my pole zero plot. Okay, now what I will do, I will place the centroid. So centroid is located at minus 1.5. So minus 1.5 is here. Okay, let me just mark that particular point and let me um, name this as centroid, which is equal to minus 1.5. Okay, so once I'm done with step 4, that is, after placing the centroid, you are supposed to draw the asymptotes. So we have 4 asymptotes. Asymptote first will have an angle of 45 degree. second will have 135, and third will have, I think, 215, and fourth will have, sorry, third will have 225, and the fourth will have 315 degrees. Okay, so let us draw the asymptotes. So 45 degree basically the diagonal, right? Say this is theta 1, which is equal to 45 degree. Sorry, I should have drawn from the same drawing. From here I should have drawn. But you use a protractor and draw the angles, okay? And then 135. So this is, I think this is theta naught, and this is theta 1, 135. And then comes 225. 225 degree, theta 2. And then finally you have theta 3, which is drawn at an angle of 300 and okay. So as you can see, the asymptotes are, symmetrically placed. Okay. So that's about your asymptotes. And then you can go for placement of the breakaway points. So you had obtained 3 breakaway points, out of which 2 were found to be valid. So the valid ones are minus 0.38 and minus 2.61. Okay, so we'll use a different color to place the breakaway points. Let's say brown. So minus 0.38, right? So minus 0.38. This is 0.5. So minus 0.38 going to be somewhere over here. Okay. And the next one is at minus 2.6. Okay. So this is 2. This is 2.5. So somewhere over you have minus 2.6. Okay. So these are the 2 breakaway points. Okay. So once you place the breakaway point, you can go to rule 7, which talks about the imaginary crossover, right? So for this given problem, we see that K marginal is positive, and due to which what happens is that you get the imaginary crossover points, something like plus or minus j omega, and the value of plus or minus j omega is plus or minus j1. All right. So similarly, you mark plus or minus j1. Um, Let us use, let's say, a different color. Say blue one we'll use. This plus j1, and this is minus j1. Okay, this is minus j1. Okay, fine. So rule 8 is not applicable, which talks about complex pole or complex zero. In our system, we don't have any complex pole or complex zero. So you can just ignore the last rule. Okay. So now let us go for the root locus sketch. Okay. So let's start from the pole which is sitting at the origin. Okay. Now in rule 3 we had predicted that the entire positive real axis is NRL section. So when we start varying the value of k from zero value. Okay. In other words, as we start increasing the value of k from its zero value, what happens is that the root which is placed at origin starts to move in the left hand side direction. Okay, red is better, I think. So this is how I can show. Left hand side direction. Okay. Similarly, the root which is placed at -1 location, okay, -1 location, uh, will be moving towards the breakaway point, right? And basically it moves in the right hand side direction in this manner. So once again, I want to repeat that the root which is placed at -1 cannot move in the left hand side direction because the region between -1 and -2 is NRL. So there cannot be any root locus. Okay. So fine. So these two roots will meet at the first breakaway point, and beyond this breakaway point, the branches of the root locus uh, become complex. Okay, so complex as in one root will move, in the upward direction, okay, something like this, and the second root will move in the downward direction, something like this. Now the question is, how am I supposed to draw uh, the complex part of the root locus? Because the question may arise something like, can I give any arbitrary shape? No, you cannot give any arbitrary shape, or the shape what you feel like giving. All right. So you remember one thing, while finding out the asymptote angle, we had mentioned the usage of asymptotes, right? So asymptotes are the guidelines for the branches of the root locus which are moving towards infinity. All right. So what you have to see that, do you have any imaginary crossover? This particular root locus problem is having imaginary crossover at plus or minus j omega. So what happens is that the branches of the root locus will cut the j omega axis at plus j1 and at minus j1 level. All right. And after cutting the imaginary axis, the branches of the root locus will move towards infinity along the direction of the nearest asymptote. Okay, so let me draw. So what I'm going to do, um, I'll use a different color so that the visibility becomes better. Okay, where's the point? Right. So smooth curve. Okay. Something like this. Something like this. You can draw, and then you will have to bend the root locus branch along the direction of the asymptote. You see, your asymptote is moving in this direction, right? Your first asymptote is moving in this direction. So let me bend the root locus branch along the direction of asymptote. Remember one thing, your root locus branch should be parallel to the asymptote. Okay, let me draw it with thick line. Okay. Similarly, in the downward direction also, same thing you are supposed to do. Okay. Because in rule 1, we have mentioned that root locus is always symmetrical about real axis. Okay. So this is what is all about the symmetry. Okay. So this is also parallel to the asymptote. So you're done with the two root locus branches. Okay. Namely, branch 1 you have drawn and branch 2 you have drawn. Okay, now you are left with the two more poles, right? One pole is located at -3 and the second pole is located at -2. Okay, let us handle these two poles now. Okay, now as you start increasing the value of k, the pole which is present at -2, it starts moving in the left hand side direction. Okay, it cannot move in the right hand side direction because between -2 and -1 there is no root locus. Please check rule 3. Okay, so it moves in the left hand side direction, so something like this it moves. Okay, similarly the root which is present at -3, starts moving in the right hand side direction as indicated with the arrowhead. Okay, once again, the root which is present at -3 cannot move along, uh, you know, in the left hand side direction due to the fact that from -3 to infinity, minus infinity, there is no root locus branch. All right. Now, after, meeting at breakaway point, what happens is that one root will move in the upward direction and the other root will move in the downward direction. Once again, the question comes, how am I supposed to, shape the root locus graph? So basically, I need to take the help of the asymptote, right? So what I will do, I will draw the root locus something like this. Okay, similarly, the symmetrical shape I'm going to produce in the downward direction. Okay, now probably you can thicken the line. Okay, so this is your third branch of the root locus and this is the fourth branch of the root locus. Okay, so this completes the root locus problem. All right, so you can replay the video and you can try to practice this problem again and again. Okay. Now in step 2, you had predicted that, see here, that all the four branches of the root locus, move towards infinity along the asymptote. Is this the case with our graph? Yes. The first branch as well as the second branch, we're moving, towards infinity along the direction of theta naught and theta 3, right? Similarly, the third and fourth branch of the root locus were moving towards infinity, you know, uh, in parallel to theta 2 and theta 1. All right. So what we had predicted, we have obtained in the graph as well. All right. So this completes problem number 1.